Why is diamond the hottest thing you own, while the gas in a balloon weighs almost nothing? Same idea behind both. It's not what the particles are, it's how they're arranged and how tightly they are held. Change the arrangement and you change everything: hardness, melting point, whether it even holds a shape. This unit links arrangement to behavior. We start with gases, where particles are so free we can write one tidy equation for them all, then tighten into liquids and solids, and finish with the great lattice types: ionic, covalent, metallic, and molecular, each explaining a material's properties at a glance. First stop the three states and the single question that separates them: how free are the particles? In a solid, they only vibrate in fixed positions, so a solid keeps its shape. In a liquid, they touch but slide past each other, so a liquid flows yet stays dense. In a gas, they fly apart, nearly independent. Heat is the referee. Add energy and particles move faster, loosening their grip. Solid melts to liquid, liquid boils to gas. Remove energy and they settle back down. So the state is just a balance between the energy pulling particles apart and the forces holding them together. Simple, and it sets up the gas laws next. Next, gases get their own beautiful law. Because gas particles are so spread out, four quantities locked together in one equation: pressure times volume equals nRT, amount, the gas constant, and temperature. Squeeze the volume and pressure rises, heat the gas and it pushes harder. One relationship governs every ideal gas. The marks here are one on units, not ideas. Pressure must be in pascals, volume in cubic meters, and temperature in Kelvin, never Celsius. Add 273 to convert. And remember, it's a model. Real gases drift off at high pressure and low temperature, where particles do attract and do take up space. Ideal is an approximation. Why does that gas law work at all? Kinetic theory. Picture countless tiny particles in constant random motion, bouncing off the walls. Each collision gives the wall a tiny push, and all those pushes added up are what we feel as pressure. Heat the gas and the particles move faster, hit harder and more often, so pressure climbs. The model leans on a few neat assumptions. The particles themselves take up no real volume, they don't attract one another, and their collisions lose no energy. Those are exactly the assumptions that fail for a real gas when you squash it hard or cool it down, which is precisely why real gases stray from ideal under those conditions. The theory even tells you when it breaks. Now solids, where arrangement does the talking. There are four structures to know. A giant ionic lattice, alternating positive and negative ions, like sodium chloride, is held by strong electrostatic forces, so it melts high and conducts only when molten or dissolved. A giant covalent lattice, like diamond, is one endless network of covalent bonds, giving extreme hardness and a sky-high melting point. Tumor, a giant metallic lattice, is positive ions in a sea of delocalized electrons, so metals conduct and bend. And a simple molecular solid, like ice or iodine, has strong covalent bonds inside each molecule but only weak forces between them, so it melts low and never conducts. Same elements, wildly different solids, all down to structure. Finally, the payoff: structure predicts property. Want to know if something melts high? Ask whether you must break strong bonds across a whole lattice or just weak forces between molecules. Want to know if it conducts? Ask whether charged particles are free to move: electrons in a metal, ions in a molten salt. Two questions answer almost anything. So the whole unit collapses to one habit: identify the structure, and the properties fall out for free. Gas, liquid, solid, ionic, covalent, metallic, molecular. Name the arrangement and you can predict melting point, hardness, and conductivity without memorizing a single data table. That's the power chemists are really after. Here's states of matter on one page. On the left, the logic, three states set by how free the particles are, and the four giant or molecular structures that decide a solid's properties. On the right, the gas equation and the two questions that crack almost every exam part: what melts high and what conducts. Your drill: always convert to pascals, cubic meters, and Kelvin before touching the gas equation, and always name the structure before predicting a property. Born-Haber lattice energies, and the finer maths of these structures come at a 2. For now, you can look at any substance and explain why it behaves the way it does.